Well, welcome everybody for another coffee session. I'm one of the hosts, David Aponte, and I'm with you with Demetrios. And we have a very special guest today. We have James Sutton. Before we introduce him, Demetrios is going to preface some of the things that we're going to talk about today.
Yeah, so the whole reason that this happened is because I was interviewing for Algorithmia, for a position at Algorithmia, and James was one of the gatekeepers that I had to go through. And and he kept trying to get me to answer this one question, and I was giving him like really political answers, I think. And then it just got to the point where he was like, but how would it actually look? What would the system design look like? How would the data move? And I was like, oh, I don't know that, man. Like, you got to go ask some engineer if you want that answer. And then I asked him, like, well, what would you do in this hypothetical situation that you put on the table? And so he explained it to me very thoroughly and very eloquently. And I thought, all right, no matter what happens with this job, which uh, it doesn't matter, because I want to get this guy on the podcast so he can explain this wisdom to all of us. And that is how James came to be here with us today. James, thanks for coming, man.
Thanks, Demetrios. And honestly, it's actually really funny is actually after we had the conversation, I actually talked to the hiring manager, and all the questions I were asking you weren't actually all that related to the actual position that we were applying for anyways. So even though I was a gatekeeper, it actually didn't influence the final decision in any case. But no, I really appreciate that.
Oh, that's hilarious.
That's funny, yeah.
Yeah, because I was talking to Bam Bam about it. Like, dude, that was a hard interview.
Like, a system design question is for an engineer, someone who has engineering experience, and that's one of the questions the type of question that you could ask for an engineering role. But yeah, that's funny.
Which were awesome questions, like, let's be honest. And so that's why we got you on here. And
awesome.
If you hadn't have asked me those questions, you wouldn't be here with us today.
Well, you know what? I'm happy I asked them.
Yeah, dude. So let's talk a bit first about you, what you're doing, like your background, and then let's get into some of these papers that you've written. And then we can talk a little bit about like maturity levels for different companies and where they sit. And also Bam Bam and I have been doing a lot of the Google paper, like, I'm not going to say critique, but just going through it and showing what Google considers like maturity levels. And so I'd love to get your take on that. And then at the end, we're going to talk system designs and hopefully go relive that painful interview question of mine.
No problem. I have that one memorized, actually. It's
you ask everybody that?
I mean, it's one of the biggest. It was one of actually our biggest customers that actually asked that was going through that systems architecture with us. So it's stuck in there. But yeah, so talking about my background. So I'm actually a physical engineering by trade or by education, I should say. I actually studied metallurgical engineering back in university. I'm Canadian. I actually worked originally as a forensics engineer for a failure analysis company for the first 2 years of my professional work-life balance or work-life experience. After that, I realized that wasn't really for me. It was interesting and exciting, but I really like to make things. And I realized that this software thing, especially in this machine learning space, you can really learn a lot if you've got time. So I actually just sat down for 8 months, but I worked on a project for about 8 months to actually not only just teach myself programming, but actually to specifically tackle a really challenging machine learning problem, which was earthquake forecasting. And I actually used data from a website called Topcoder, which is kind of like an older version of Kaggle. It wasn't really as well defined as Kaggle is for specifically the data science machine learning problem space. But I eventually actually built an actual machine learning model that actually this predated Caffe, this predated TensorFlow, predated PyTorch, which required me to actually build out my own machine learning framework to actually be able to get that to work. And with that, I actually I wrote a little blog post on my own personal blog, which I haven't updated in a while. And I use that as kind of part of a reference to apply to Algorithmia, which is my current employer. And that was about 4 years and 9 months ago, I think, something like that. So they saw that, they were interested, they wanted to learn more. And that's how I actually got started. Algorithmia is essentially my first software job, and I've been there for almost 5 years. So I guess that worked out pretty well.
That's awesome. I think just I want to comment on like that. That's a great example of how to break into the field. People often ask me, what do I need to learn? I'm like, it's you're maybe not asking the right questions if you're so focused on every little concept that you need to know. There's just too many, right? You're always going to deal with new ones, but take on a real project that you're interested in, and you're going to come up with so many problems. Like there's going to be so much shit that happens along the way. And as you deal with them, you're going to have to learn something new. And that right there is like one of the best ways in my experience to actually not only learn something, right? But to like break into a new field. It's real concrete experience. You have a lot to talk about there, But yeah, I just wanted to comment on that one thing. I thought that was great.
Fully agree with that. Actually, one of the big things that I always recommend is to find something that's harder than you know how to solve today, and just give yourself time to be able to tackle those things. You're definitely going to stump yourself potentially for weeks. Sometimes I think there was at one point where I was actually blocked for almost an entire month on one particular thing that I just couldn't figure out. But honestly, that perseverance is probably one of the more valuable traits that I've seen for software engineers now that I'm actually on the hiring side of things. And if I can see that in anybody, then that actually usually trumps almost everything, including current skill sets. So
yeah, it's invaluable, right? And I've seen this when I was teaching little kids how to program in Python, that they want to be able to do all the cool things, right? They want to be able to build all these things, but I'm like, it really takes perseverance with failure. Like you're going to make a million mistakes, and like being comfortable with that and not like giving up when that happens, like looking for the answer somewhere or learning about that, that right there is part of what learning is all about, man. Persevering through that. So you're right. I think that is a very important characteristic that I look for in other engineers as well. Like, are you going to be able to work through things that are unstructured, not well defined, and messy, which is real life, and persevere?
Yeah, this isn't a university class. It's not going to have a well-defined objective, typically.
Yeah, well, I love this wisdom. Let's talk a little bit about these papers that you've written. And I know Bam Bam was mentioning earlier before we started recording about...
It's so funny. No one else calls me, my grandma calls me Bam Bam. And then you go, the beaches over here, Bam Bam. But yes, Bam Bam. There's one awesome article in particular. Go ahead, sorry, Dimitri.
Tell us about this awesome article, the KD tree.
Yes. So there's this cool article on, so there was a one-shot classifier, if I remember correctly. And we can define what that is in a second. But there was some memory constraints, if I remember, or latency constraints because of the lookup. You had some embeddings. And so using a KD tree, which is an interesting data structure, you can actually really make things a lot faster, more memory efficient. And there was some other cool things that he talked about there as well. It's written, and there's some Scala code in there. So for anyone that's interested in that, it's really interesting. I don't have it in front of me, so I don't remember everything. But James, can you, just give me a refresher on what the gist of that was there?
Yeah. So as you said, it was talking about a one-shot classifier algorithm. Specifically, the one that we actually built on the platform was for document classification. But the overall concept and the tools and techniques would actually be generalizable. So you could actually use those for images or videos or any kind of concept that you could convert into an embedding. Taking a step back, talking about maybe what an embedding is and maybe what Word2Vec is, I guess might be worthwhile too. So an embedding is a fancy way to describe kind of an internal representation or kind of a new way to describe in a piece of information. And that information could be really pretty much anything that you want it to be. But typically what it's doing is it's describing information in something that's a bit more concise. So it's a little bit less, there's a little bit less dimensionality to it. Typically, of course, the actual footprint of it, like from a physical perspective, is usually a lot smaller. You can kind of almost think of it to some degree from a layman's perspective as something like almost like a zip file, like you're literally zipping something up and it's become smaller. And if you take a look at it, you might not be able to understand what that is, just because it's, of course, if you zip up a document, it's going to be a whole bunch of binary data. But then on the other end, if you unzip it, you can actually see it again. But that zipping process is similar to kind of how an embedding is created. The big difference is that in a zip file, that kind of that representation that you look at, if you just open up a zip file in, I don't know, a text editor, that doesn't really have a structure that you can use. However, funnily enough, with machine learning algorithms, you can actually create a machine learning algorithm that can create this kind of smaller representation of that, whatever your input sequence is or your input data set is, and be able to actually do stuff with it. Like, for example, you can actually walk over it. You can say, hey, you know what happens if I tweak this specific number here? What happens if I tweak this number here? And that actually has a direct correlation back to the original kind of data. So for example, if you're working with images, sorry about that, I've got dogs in the background. If you've got images, for example, and you want to, for example, kind of just say, hey, you know what, I'm going to pass an image through this embedding generator or feature extractor or image to vec algorithm. There's so many different ways to call these things.
Yeah, that's so true.
Yeah, I don't know why they have so many different names, but they do. I think it's just because of the different backgrounds that people come into the space and use the same tools.
Exactly. Yeah.
But in that image, with that image, if you actually pass that through one of these embedding generators, and you get an embedding on the other end, you could actually walk over that and say, you know what, let's just tweak one of the numbers on one of the fields, and then regenerate that or an image on the other end. And you can actually, for example, like say, hey, you know what, I'm going to remove a hat, or I'm going to change the color of somebody's hair. You can actually have an embedding that actually has real world implications in regards to what the actual different dimensions in there actually mean. So going back to word vectors, they're actually kind of the prototypical kind of example. In that space, you can actually do, you can actually do word arithmetic. So you could actually do, for example, something like king minus queen, if you actually do that subtraction embedding space and return that back to the real words, I should say, you can actually end up with things like royalty, or with gender, or with other kind of components that actually relate to those specific meanings.
Oh, wow.
Yeah, it's pretty crazy, like why the math works. I love, like, I still am like fascinated by it. Like, it just works, you know.
Yeah.
Like he was mentioning, you know, you can find similarity between things, and the fact that it's a useful representation is like funny to me, you know. Like, it's still like, wow, like, yeah, like you jumble up a bunch of numbers, you compress them, you could play around with them, try this out, try that out. But yeah, one question I have is, why is this a challenge from, let's say, the engineering perspective with deployment? You know, so you have a model that's let's say a document classifier. That's a good example. Why is this a problem from the deployment perspective in your experience? Or why the need to use you know, a data structure to help solve this problem?
Yeah, it's a great question. So it's actually really interesting because from a machine learning perspective, the actual that inference process, or that kind of creation of those embedding vectors, is actually very fast. However, due to the fact that we're using machine learning, nothing's really quite as simple. And the real big problem is the fact that when you're actually generating you're creating that model, you're training that model to actually get something that will actually give you good, valuable results. It typically requires to actually have a pretty large footprint from a model perspective. So it's going to have a lot of parameters to be able to understand how to convert your input representation into some kind of internal useful representation. And that typically isn't necessarily a big deal if you just have something kind of just running in an EC2 instance, set up with a Flask app or something like that, just to kind of work off of some requests that people come into your personal blog or something. But if you actually want to be able to scale that, it's a little tricky, just because that model file, that can be upwards to around 3 gigabytes sometimes. So for example, Word to Vec, I believe by default is 3 gigs, which, I mean, the speed of light is only so fast. And it's, even if you have it on your disk, being able to deserialize that and actually convert that into, like, for example, I don't know, Spacey or NLTK or TensorFlow's kind of internal model representation, and actually store that in memory, that takes time. And if you haven't,
sorry, go ahead.
I was going to say, if you haven't spun up a new machine kind of to handle that new scaling process, that can take sometimes up to 30 minutes. To kind of download that file and then convert that and get that ready for inference.
And I was just going to say that, there's different types of ways, like bottlenecks, right? They could be CPU bound, right? It's something that you can deal with, like using a better processor or even an accelerator. But if it's IO bound, you have to pull it out from disk or even pull it from S3. Like the other day, we had this huge prediction file that was literally like 4 or 5 gigs, which is really not that much. Like that could fit in memory for most modern day computers. But if you have a service, right, that needs to, respond in less than 2 seconds, then it actually becomes a big problem. Like you mentioned, scaling that. And if you're getting a lot of requests and you, let's say, for example, need to make replicas of that service, and then you have to partition the data in some way, like things can get hairy as you deal with more at scale. So something that was originally quite simple, like, not quite simple, but, I feel like today most practitioners are familiar with embeddings. Like they've at least come, into contact with it once, but dealing with it at scale, probably not. That's something that's a new problem that we're learning how to deal with, and in particular from the deployment side.
Yeah, and they're useful. They're actually useful in a lot of different industries. Just the fact that you don't actually necessarily have to train a brand new model every single time to be able to actually take advantage of these things. So taking a step just kind of forward before we dive into how we kind of rectify that issue. Embeddings can actually be used without necessarily actually having to train anything. You don't actually have to train anything after you've created that embedding model, because as with document classification or word classification or image classification, the big thing is you're trying to find a way to separate different types of entities and say, hey, you know what, these are dogs, these are cats. And thankfully with embeddings, by their nature, the fact that they preserve that kind of conceptual capabilities of like, oh, we actually understand what a cat is, we know what a dog is. There's going to have that separation in that embedding space that you can then kind of go and look and say, hey, you know what, actually, I'm going to have a single label of cat and a single label of dog. And you will really, for a lot of use cases, only need that. You only need 1 and 2. And that will be enough to actually be able to say, oh, this is closer to cat, or this is closer to dog, just because of how your embedding generator actually preserves that kind of conceptual understanding of what cats and dogs are. So going back to the problem space that we were talking about, so we have this really, really big file, we have this really, really big model, and we have to get that ready. And as you're saying, inference, especially from a documents classification perspective, we definitely want that to be fast, because we're not actually just classifying or creating an embedding for a single word. We're creating embedding for potentially hundreds, if not thousands of words.
Yeah.
And just for a single document. Which typically you're not passing in 1 document at a time. You might actually be passing in maybe a batch, like 100. So that number starts to jump really, really, really quick.
So it sounds like it's batch inference at live inference. You're doing at least from that use case, or am I misunderstanding? Was it just for a few examples at a time?
Well, the big thing is it can be for multiple users at once. So for example, at Algorithmia, we actually have a shared tenancy environment. Which means that other people can actually interact with those algorithms as they'd like to. And in those environments as well, because we actually have a system to kind of preserve data privacy and to preserve the security and kind of sanctity of not only your data, but your model. Each of those, if one user calls the algorithm and another user calls the algorithm, both of them are going to spin up new instances themselves. We're not going to share those just because, of course, some things could leak. So that actually kind of contributes to the issue of, hey, you know what, we have to run these jobs. We have potentially we're going to have burst requests come in. We might have nothing coming in for 20 minutes, and then all of a sudden we have 1,000 documents that we need to process all at once. And that can be really tricky when you have to wait 30 minutes for a scale-up process, right?
Yeah.
So
how did you guys? Yeah, go ahead, Demetrius.
I wanted to just talk for a second about the bottlenecks that you mentioned, David, and you were saying there's so many different ways and areas where you can encounter bottlenecks. I'm wondering if there's can you give us a few of those and how you've seen them, and then maybe how they can be overcome?
Yeah, for sure. So we were just talking about IO bottlenecks. So that's really around time of flight, just passing files between systems. And I'm going to be talking about as a potential solution for that next. But definitely there's like, for example, CPU bound issues where you have a single core processing something, where you're running maybe a batch load of requests. And that can actually really slow things down. However, of course, if you have a multi-core system, you can actually, of course, depends on your use case. Sometimes if there are kind of if there's interdependencies in your data, it can be tricky to kind of parallelize that.
Yeah, race conditions and things like that, deadlocks, exactly. All that.
You can definitely still parallelize those. For example, there are sorting algorithms that are actually great for parallel data processing. Bitonic sort, if I remember correctly, is the one that I actually used in my earthquake forecaster, for example.
Oh, cool.
Yeah, I had to implement that one because there wasn't an example of that in the libraries when I was working on it. So there definitely are ways to parallelize things, and you can definitely parallelize them onto CPU. But sometimes you can also actually parallelize them on GPUs too. So depending on the use case, depending on the problem space that you're working on, if it's like kind of a math processing system, like you're doing like matrix multiplication, kind of the prototypical example. GPUs are great at that because those are highly parallelizable. There's no interdependent requirements between each of those matrix multiplications. So you can actually do them essentially all at once, which is great. So you can really get a dramatic improvement in throughput. But then, of course, from a GPU perspective, you can also have memory issues. So anybody who's played video games in the past 10 years, you probably ran into issues where you're like, oh, my GPU doesn't, this game is too GPU intensive. I'm actually getting like out of memory exceptions, or you get like a blue screen on your Windows. That's just because of the fact that GPUs don't really page memory very well. So in the host machine on most computers, they have this concept called paging, which is kind of nice. It allows us to actually use your disk to be able to say, hey, you know what, you use too much RAM. You're overloading your RAM. And instead of just turning your computer off or saying we can't process your requests, which is not really what you want, you can actually, it'll start to use your hard disk, which isn't optimal. It's not very efficient, but it will work at the least. GPUs don't have that, at least not out of the gate. And that can definitely cause some issues. But thankfully, of course, there's a lot of, that's the known problem. And there's a lot of tools and systems to be able to kind of rectify and get around that. In most modern machine learning frameworks, for example, they have things called data loaders, which actually allow you to buffer data into the actual GPU. So for example, if your model memory is like half of the footprint of your GPU, you can actually buffer input data into your GPU and buffer output, the results out without necessarily having to have everything fit all at once. So that's definitely something that I've ran into on a regular basis with some customers. It's like, hey, I'm getting out of memory errors. How do I deal with this? I'm like, oh, use a data loader.
Yeah, I'm actually using that right now. I'm chunking right now because the data is just too big right now. And it's like not the best, but it does work. Another thing that's helped in the past is downcasting. Like I found that just, pandas or like some of these libraries do a lot of things for you. This is for like the Python folks, right? And you don't really have access to some of that underlying stuff. You're not really doing a lot. So it optimizes things for you, but sometimes it can be pretty clunky. So I found just by actually going and like playing around with the data types, downcasting them, that also helps too. But yeah, just want to throw that in there.
Yeah, like for example, TensorRT is actually a great framework that's made by NVIDIA that actually does exactly that. That allows you to downcast types. So instead of using doubles all over the place, it actually downcasts. So I think actually I'm not going to remember this. Somebody's going to yell at me over this. I think it's like it's like short floats. Is that what it is? I think.
I feel like it's a float. I feel like most things are a float, right? Because I forget why. It's like for some computer science reason.
Yeah, if I remember correctly, it's just due to division errors, because if you actually have integers and the numbers are too big, you can actually end up getting zeros. But I believe it's short floats.
Somebody will tell us in the comments.
Somebody will tell us. I forget exactly what it is. I should know this because I actually have implemented many examples using TensorRT and actually did examples of it, but I forget what it is right now at the moment. But yeah, so those are definitely things that I've seen on a regular basis. But yeah, going back to the example that we were talking about, because I do want to kind of walk through that because there's a lot of pieces there. So what we did is, so again, we had that issue with the footprint was just too big. It was a 3 GB model file. But then we realized that, hey, you know what? The actual English language actually is kind of finite. Like there's only so many characters for that in the most part. So instead of actually using this machine learning model as a machine learning model, what we actually did is we essentially converted it into just a lookup table. We said, hey, you know what? Let's actually just create like for every single not character, but every single kind of token in our model that the model actually is trained on, because of course we actually have to predefine what those tokens are in advance for any kind of natural language processing task. We actually just created essentially this big massive lookup table. And you can kind of almost think of it like a Python dictionary, where you just have this this key, and then it has a value. And what's nice about that is we can actually start to split that. So what we did then is we said, hey, you know what? This is actually if we want to make this efficient, we can actually convert this into a tree and kind of use an indexing system. So inside of Algorithmia, we don't necessarily have a native kind of database system. And that's actually by design to some degree. We want people to be able to have the flexibility to integrate their own databases with the platform. But we do have a native block storage system. So we can kind of just use this block storage to kind of act as this index management system. So what we did is we actually, we realized that, hey, you know what, we have all of these characters, or we have all of these keys, and they associate them with the values. What if we make a prefix tree that actually goes and says, hey, everything that starts with A, let's look over here. Everything that starts with a B, let's look over here. Everything that starts with a C, let's look over there. And we started to create this tree, but we didn't complete the tree. And this is actually very similar to that KD tree example that we're going to talk about in a second. But what we did is we actually just said, hey, you know what? If there's 500 elements in this side of the tree, in this branch, let's actually just save that as a file. So all of those components, let's save that as a file. Let's upload that to our block storage, which in this case was S3. And then let's actually store that path inside of the tree, which converts that tree from being an actual full tree, which has branches that all get on the leaves, to an index, which we can then actually go and do a lookup. So we can actually just go say, okay, we have a key, we have, say, for example, I don't know, the word the. Let's actually go into this, let's download that index file, which is only like 10 kilobytes or something like that. It's super, super tiny. Let's go through it. Let's traverse down the T, then the H, and then find out, hey, you know what, there's only like 50 words here in this bucket. Let's go and download only that bucket. So that really, really speeds up the process, because instead of having to have that 3 gigabytes of data downloaded every single time, now you can actually skip that and essentially really sometimes get less than a megabyte worth of, use less than a megabyte.
Oh, that's
worth
so
of bandwidth.
cool.
Yeah, I think this is so cool, because this is like really like computer science applied, right? Like data structures that are actually useful. So I want to parse some of the things there for anyone listening, because these are things that I like to geek out on. Like, so for example, why is a tree useful? So some things there, like for example, that you mentioned, it's like a dictionary. So I like using dictionaries, so I get constant lookups, right? I can get something in constant time. So for anyone familiar with big O notation and stuff like that, or omega, there's a few different words for that, but yeah, it helps with that. And another thing that was really interesting was you mentioned it basically, so you're using it as an index, which is a pretty old technique, right? One of my line managers was telling me about search engines, right? How using a reverse index can drastically improve performance in that. And so how indexing is like, you know, it's a pretty, not old, but like it's been around for some time. Oh, good. But it's been around for some time, but something like that can really help and make the performance of something a lot better. But I guess what I'm trying to get better at over time is making that connection between, oh, this works here. And it's like it's all there. I'm sure a lot of us are familiar with some of these things, but then it's making that connection. And I love how that's a great use of data structures. You know, it's a great use of those concepts.
It's morning over here.
I love dogs.
Yeah, it's been cool. We've been seeing the sunrise in your window behind you as the morning starts to happen.
That was actually intentional. I was thinking about that last night. I'm like, that might be a cool
Oh, clutch.
Well, man.
So yeah, we could keep. Yeah, go ahead, Demetrius.
I was just gonna say let's transition into tooling a bit, because I know you have a lot of experience with using different tools. Of course, you're working at Algorithmia and they're one piece of the puzzle, but there's all kinds of other tools and different things that you've seen along the way. So I'd love to hear just a bit about what you've seen that works really well, and maybe some different tools that you've been really interested in, if you
Yeah,
can tell us.
yeah, for
Of
sure.
course, I know for you, Algorithmia is number one. We're not we're not saying that any other one is better, but yeah, give us a your vision of the landscape right now.
Yeah, sounds good. So there's definitely, I think, two different kind of universes when it comes to tools in this space. So from an MLOps perspective, of course, the real focus is on enterprise and is on bigger companies that are saying, hey, no, we actually have to we have to manage this stuff in production. We actually have customers. This isn't just some kind of project that I have on my personal blog or something like that. So that it doesn't matter if it's not working. Reliability is a pretty key component. But it is also interesting too, because there's now kind of becoming this intersection between the toolings the tooling systems that a lot of practitioners and kind of data scientists are using, and the overall kind of MLOps reliability productionization kind of problem space. Like there's a lot of these companies that are kind of migrating towards that space. So for example, Anaconda is a very, very, very popular data science and just overall Python, I guess, platform to allow people to write or to be able to manage their dependencies more effectively. And Anaconda actually has their own serving system to be able to actually serve and maintain those environments. Same thing with Jupyter. There's Jupyter notebooks are very, very popular with data scientists. And those Jupyter actually has its own serving system, and actually Google actually has its own native serving system as well, called Google Colab or Google Serving. So there's a lot of these systems that are kind of like the tooling is starting to realize, or the tooling organizations are starting to realize, hey, you know what? We shouldn't just be focusing on just allowing people to make machine learning models. We should actually start focusing on, hey, how can we start to productionize, and how can we start to add reliability and maintainability into these systems? So in that way, Algorithm is actually what was way ahead of the curve, because this is something that we've actually been focusing on for the past 4 or 5 years. We knew that eventually, as tooling matured, as organizations matured, that they'd start to realize, hey, you know what? I can't just run. I have this TensorFlow model running in a Flask app, and I have that running in a production environment. That's not going to work. Eventually, that's either going to have one of two things happen: that Flask server is going to turn off for whatever reason, or B, you're actually going to get more requests coming in than your Flask app's going to be able to handle, and it's just going to fall apart. And that's actually, funnily enough, something that sometimes customers kind of start with, and then they realize like, oh, hey, we actually need to use real systems. We actually have to start to use the tools that are actually designed for this purpose. And that's really where the machine learning kind of ecosystem has been going in the recent years. And especially in 2020, I think there's been a big movement towards thinking about machine learning operations, and kind of thinking about it from like, hey, you know what, we need to not only just make this work in our system, but we need to make this work in an actual real kind of production environment.
Yeah, make it work at scale and make it bulletproof so
Yeah,
that
exactly.
we don't get into any trouble down the line. So awesome, man. Well, let's talk about this Google paper. I'm not sure if you've read it, but I imagine you understand the gist of it.
Yeah.
And the whole idea around it is grading the maturity of how people do things and how much automation is involved in the pipeline. And also they have the Google maturity test. And so really what I wanted to ask you about this is, because there are, as you talk about, okay, enterprise teams that you may think that they're mature, but once you actually start seeing what they're doing, it's not as mature as what you would expect.
Yeah.
And so I'm just wondering, like, what is your take right now on the whole idea of maturity, and
Yeah.
also the how you've seen the different ways of maturity play out?
Yeah, it's a real thing. Different companies are approaching the machine learning universe from different angles. Some of the smaller, scrappier companies, especially that are kind of being born into the machine learning world, generally have an advantage, of course, just because of the fact that they are more nimble. So they are able to not only just build out their machine learning models, but they have this concept of productionizing these models built into their overall fabric of the projects themselves, saying, hey, you know what, not only do we need to make this, but how can we make this repeatable? How can we retrain these models? And how can we ship these in a way that's reliable, maintainable to a production environment? So those companies generally have an advantage in that space, but they're definitely not alone. Some of our biggest companies, customers, for example, actually are very, very, very mature, and have, fun enough, been able to. We give them some suggestions on some, like, for example, CI and CD pipelines structures, which for everybody at home is continuous integration and continuous deployment, which is just a really fancy way to say, make sure that everything tests. You have automatic tests, and that nobody's actually manually deploying things anymore. You kind of automate those things. We send them some examples, and they've actually gone and kind of taken that and ran with it and built out a very, very, very robust machine learning deployment systems. So there's definitely a lot of maturity there, but the vast majority of companies that I've seen up to this point, they're still working on that. It's still a work in progress. They typically have a lot of big companies will have their machine learning engineering teams. They'll have data scientists. And those teams will actually have built stuff. They'll have things that actually work, that they can actually show in presentations and say, hey, look at these numbers. If we can only get this running in production, we'd be great. But that was one of those things that for a lot of companies, they weren't really thinking about that back in the kind of the early days. I guess maybe when I say early days, probably about 3 years ago, I guess is kind of that time when people started to take machine learning seriously. When they started to say, hey, you know what, we actually need to get into this machine learning space. Operation and productionization just weren't words that people were using back then.
That's fascinating. Yeah.
One thing that we noticed is that, the paper really has such a huge emphasis on automating everything. And, I totally understand that from the DevOps perspective and just treating it like traditional software. But for a lot of companies, that may not be, sorry, let me take a step back. It also talks about the need to continuously retrain. And there's a lot of emphasis there, because if you need to adapt to a constantly changing world, let's say your use case requires you to have the freshest data still, and this is actually a problem for you, then it makes sense to retrain your model and do some other things to alleviate concept drift. But for other organizations that their models don't need to be updated as frequently, for example, the document classifier, I assume that you probably wouldn't have to retrain it that often or generate those embeddings. Maybe, I don't know how often you would need to. I don't have any good estimates in my head, but I know from Benevolent with our knowledge team who does all the natural language processing, they don't often have to generate those dictionaries like all the time. Maybe like once every couple of weeks or something like that.
Yeah.
It's there's some reason for it, right? You're trying something out or you're doing a change, but it's not something that in their mind there's like a huge need to automate all of that. What are your thoughts on that? Because I know that, there's a lot of pressure from these smaller companies to look at these, paper like Google and be like, damn, I'm like at the bottom because I don't automate everything. But I don't know, just curious to hear your thoughts around just that.
I actually think it comes from a maturity perspective. When you actually do have, like when we're talking about these mature kind of systems, they have these things in place. That maturity doesn't necessarily come from just being agile or kind of knowing that they're going to need to have these production systems ready to go. They've typically came up with a solution that works. Like they found that product market fit of their ML model, so to speak. They found how that's going to work and how that's going to be useful. For a lot of machine learning applications, especially early on when you're kind of still like if you're a startup or if you're in a kind of an incubator inside of a bigger company, kind of just exploring what's possible. Explore what's possible. Don't try to automate anything until you've actually found something. That's a big thing, because if you try to do that early, then you're going to restrict yourself prematurely, which is one of the last things you want to do in a space like this, because
Absolutely.
it's definitely, there's engineering components that you can add to it, but early on, it's a lot of research. And that's really the way that you should think about it, is like you start off doing research and then it swaps towards engineering once you really find that thing that makes sense.
Ooh, great point. Start off doing research, then go to engineering. As
it's kind of it's not like a if this or that kind of thing. It's not like a binary, but it's kind of a gradient. Like you kind of add more engineering as the systems that you're building kind of start to get more mature. You realize there's traction, this tooling works, the customers that are being serviced by this love it. Like once those things start to happen, that's when you start to add a little bit more of those processes. That's when you add, for example, the automation around training, say retraining systems. For example, at a Word2Vec, you would actually want to retrain that on a regular basis, because, for example, if you used a Word2Vec model that predated 2016 or 2015, and you used the word Trump, for example, it would probably relate to a playing card. Whereas nowadays, people don't think of that. That's not really the correlation that most people think of.
Great point. Yeah.
who do they think of?
The president of the United States. But yeah, those kind of sit like, so thinking about from that perspective, saying, okay, no, let's add process little by little by little. And eventually once you get, of course, Google, I mean, it makes sense from Google's perspective because they've been doing this longer than anybody. They've been working in the machine learning space longer than I can't imagine any company that's been playing with this before them. I think they hired all of the original neural network designers and architects. So they've been working on this for a really, really long time. So when they come out with a paper saying this is how you do it, they're saying it from their perspective. And the part that's missing is saying, but don't do this from the start.
Yeah.
Yeah, that's a huge point. Yeah. Yeah.
Dude, well, let's jump into that a little bit more, and these like the system designs for MLOps and what common patterns you've seen in the system designs, at the risk of overgeneralizing everything. And I do understand that each use case has its own way of going about it, but just maybe some patterns that you
I can talk about an actual use case. I can't talk about it in an extremely deep detail, but I can talk about a few of them. I just won't associate them or mention any customer names.
There we go.
But for example, there is one that's always really topical, and we actually talked about this, Demetrios, which is around kind of network anomaly detection. So a lot of companies, especially big ones, they have a lot of devices. They have a lot of computers. They have a lot of servers. They might even have a lot of mobile devices. So they might have a lot of employees that are actually using their phones. And it can be a huge amount of work from a security perspective to be able to actually manage those and to maintain those. So what a lot of these companies will do is they say, hey, you know what, let's start off with like a heuristic model to be able to kind of aggregate all of that data and then kind of have some rules kind of defined. But a lot of companies, and some of the companies that I've worked with, are actually moving towards a machine learning approach to be able to detect those anomalies. And as you can imagine, for some of these really big companies, the data size gets ginormous. And this is a real-time problem, right? Like this needs to be done within the next 5 minutes. It's not great to be able to detect an anomaly that happened last week. That's not really all that practical, especially if you're like, for example, in the financial services or kind of the fintech kind of universes. Like that's really bad. You want to be able to
lose money
really early. Yeah, exactly.
Yeah, you lose
or
money.
Customer trust or customer confidence, or it could be a massive scandal. You might even get sued. Who knows? There's a lot of different things that could potentially happen there. So what they do, like in this kind of example, is they on a regular basis have like a streaming pipeline, like a Spark or Kafka that are kind of listening to or reading output from a stream aggregator, and that could be something like Kibana. That could be something like everything could be stored in Splunk. There's a lot of different places where that data could be stored. But it's interesting is the step immediately after that, where we're taking a look at, like, for example, the last 4 hours worth of this log data. And that amount of data could be something like 7 million to sometimes upwards to 100 million data points, which is a lot of data. That's not going to be very useful for a machine learning model. So what they do is, for example, like every so often, they'll take a snapshot of that time. they'll pass that into some kind of processing system to be able to transform that data from being, for example, 100 or 100 million data points to a single data point. So they have, for example, some kind of way to generate features based off of that. And then, of course, once you have this data point, you need to process that using a machine learning model. That machine learning model can be, of course, inside of, if this is Spark, this could be inside of Spark ML pipelines, or this could be inside of some kind of external tool, like, for example, TensorFlow or PyTorch running inside of Algorithmia or one of our competitors. And that output from that, so that, of course, that model is really just detecting, hey, you know what, like, is this an anomaly? There's many different ways to detect anomalies. You can just have a simple regression model. You could even actually have something a bit more interesting where you're actually doing a forecast-based anomaly detection system, where you're actually you're calculating the reconstruction error based off of what you forecasted and what you actually saw. So there's a lot of different ways to do that. But typically, that's kind of the workflow that we've seen for a lot of those, like, really robust production-ready kind of workflows is something like that. From a tooling perspective, like, or from a requirements perspective, like, typically the number one thing that almost every single customer that we ever work with is looking for, the priorities are reliability, speed, and cost. That's typically the order too for a lot of them. Like, the reliability is by far the biggest reason why they're coming to talk to somebody for dedicated deployment and model productionization as a service, because they've tried to do it themselves, or they've thought about this for a little while, and they realize that, hey, you know what, that reliability, that's actually going to really hurt us if that's not reliable.
Yeah, one thing I want to bring up is that there's sometimes some trade-offs there, though, no, right? There's something that comes to mind is like the CAP theorem. So like consistency, availability, and with partition tolerance, right? So like it's very hard to have all three of those things, right? Like if you want to have fault tolerance, you create a bunch of replicas. So if one thing fails, you have another one as a backup. But then if you have some shared state there, then you have to deal with some of the challenges of consistency, right? And then if you want high availability, right? Like there's a difference between it being like on, it's working as it should, and it's available, meaning it actually can take new requests as they're coming on and scaling up. And then like the cost thing, in my mind, I bet you guys deal with this a lot with your clients, right? Is that you want all of that, but for the cheap, right? You want it to scale up when I need it, scale back down. I want it all taken care of, but I don't want to spend that much money. But there's some challenges there, right? Like how do you go about these discussing these trade-offs with your clients, and helping them understand that no matter what system design you have, there's going to be some bottlenecks, some trade-offs that we have to make, and we can do our best to kind of make them better over time. But yeah, anyways, I just wanted to touch on that.
Yeah, that's a great point. There's definitely a ton of those. Thankfully, to some degree, there are tools in the space for all of those different segments that we we're just talking about. So like the stream processing, for the data aggregation, for a database that might actually be storing some of these some of the actual data that we're getting, like the logging events, for example. And thankfully, there are tools that are really well suited for those individual kind of components. And you don't necessarily have to make dramatic trade-offs if you're using the best of breed for each one of those different systems. If you are, of course, using kind of like an end-to-end system, then you really are kind of stuck with how you're going to be able to kind of optimize for those different pieces. But of course, every single one of those sections, when we're talking, each customer is going to have different requirements for each one of those different sections. So it's definitely a combinatorial explosion kind of problem space. It's like, okay, for this, do you care about high availability? And it's like, well, I mean, if we have 100 million data points and we lose 5 million, well, that sucks, but it's not the end of the world. Like we have a huge amount of data to work with, and as long as our the feature, like the actual vector at the other end, doesn't get affected that much, and the actual overall the overall reliability of our score is good, then it might actually be okay if we don't actually always get the same kind of exactly consistent set of data every single time you do processing. But if that is different, if that actual result on the other end, it does change, then it's like, oh, actually, we do need that to be incredibly consistent in that case.
Yeah, like you mentioned finance, right? Like they're like, if I'm remembering correctly, a lot of them like need ACID compliance. I forget exactly. I think like their data needs to be like so easy to audit and have to like, share with people. So like, exactly, like for some use cases, it's actually, that's like the most important thing.
Yes.
Like we need it to be a consistent above all else. For other ones, it's like, well, we could afford a couple, lost data points here and there. And it's identifying those things that is, I think, a part of developing a robust system and iterating through as you encounter new issues.
Yeah, exactly. When it comes to the actual algorithmia product, it is also an interesting piece too, because as we were talking, every customer is different when they come to us for the specific requirements. Some of them have PII requirements that are like, hey, we have personal identifying information. We don't want anything to leak at all. We don't even want to have logs of the inputs and outputs from our algorithm requests. I'm like, well, and what if you have an exception? What do you want an exception to do? It's like, oh, just give us a generic exception message. We'll figure it out. I'm like, oh, okay, we can do that. And that's actually something we didn't even design for that in the system. Like that wasn't even something that we really thought of. It's just one of those things that as we kind of grow our customer base, that's something that like, oh, that's really interesting. We're definitely going to add that as a feature. That's really something that we're going to start thinking about because, oh yeah, PII, the types of companies in that space, that's their most important thing. Like cost is like, oh yeah, it'd be great if it was cheaper. But like, it's like that, like, hey, can you handle that? Yeah, cool, we're done. That's great. That's what we're looking for because very few other companies in that space can do that or other tools in that space can do that.
Well, I think this is a perfect segue into the interview question because I remember you mentioning about PII and like, how would you deal with the PII? And I was just like, I don't really know. And so can we break that down real fast and can you go into it?
Let's do that. Yeah. So just for
How do we
everybody
frame the problem again? What exactly was the question?
The question was, I'm a business. So it was actually an interesting kind of role play kind of problem. I was playing a business. So I was one of these companies and I was asking Demetrios, we definitely love to have you help us kind of how to figure out how to optimize our machine learning models and our machine learning workflow. But our data actually has personal identifying information in that. How would you be able to help me if I can't actually send you the actual real models or the real data because there is personal identifying information? Taking a step back, when I talk about personal identifying information, that might actually might seem obvious, but it actually isn't. There's a little bit of nuance there. When it comes to like GDPR and stuff like that, personal identifying information could actually just be your IP. It could actually just be your IP plus some other kind of piece of information. It could be a username or a unique identifier for a user plus something else. That could be enough to be sufficient to be called personal identifying information for one of these regulated industries. So there actually is something that we run into on a very regular basis nowadays is people coming to us and saying, hey, we have PII, we actually can't share this stuff with you because we're not allowed to from a regulatory perspective. So in that instance, when we are working with customers that have that kind of have that kind of data and are looking to leverage algorithmia or leverage our product and kind of understand how to have best practices and how to actually convert their potentially monolithic model or maybe some other kind of architected kind of machine learning workflow into something that will work in algorithmia. It's an interesting challenge because typically we will actually, a lot of the times they'll just pass it over the fence and say, hey, this is an example of it. If you can get this to work, then we're good to go. Because that's typically the easiest way to do it because we have a lot of experience doing that. We've been building these, what I call bridges for a long time because the first kind of machine learning model that you actually get running in a development environment is always going to be the hardest because every single other one afterwards, you have an example to work off of. And every company does it a little differently. So it always requires a bit of nuance and work there. But with PII, you can't do that because they're most of the time they can't even send you the model. They sometimes can't even send you the architecture of the actual model itself. So it's tricky to kind of do that. And in those instances, it's definitely going to be a much more of a collaborative kind of approach. You're definitely going to be working with their engineers. You're working on your end. Typically what I would do in that instance is I would walk through the process of figuring out how to create a replica, how to create kind of a dummy version of what they're looking for. There's an example that we did relatively recently around duplicate image detection, where they were processing millions and millions of images every month, and they wanted to be able to detect if an image was duplicate. And that data was PII, so there's no way that we could actually get real data from that. But we're like, hey, you know what? Like, is there a way that we can at least like just verify that this technique works? And of course, there's images all over the internet, so we can use those. And of course, it's not going to be the exact same representation of data that they're actually going to be using on their end. Of course, if it's going to follow a very concise kind of expected kind of flow, then we might not be able to replicate it perfectly. But image generation is actually relatively easy. You can generate a whole bunch of fake images really quick. If you want to, you can actually just generate random noise coming from your random random on Linux or on Mac. You can actually just pull information from there and just create static images, thousands of them, hundreds of thousands of them in like less than 5 seconds. So that's kind of a way that we've been able to kind of walk through that space. But then, of course, once you have a replica, that's not really going to be very useful because it's, of course, not the actual real example. So then what we do is we typically would have to go and give a demo of kind of like, hey, you know, this is the architecture. This is the problem space that you kind of showed to us. This is the representation of what that would look like on our platform. Here's all the documentation, everything. Give it a shot for like a few days, and let's have a working session next week or something like that to kind of continue to iterate on that. And that's actually been very successful. We've been very successful with that kind of model. But it's definitely not something that you would think of kind of off the cuff. If you've never kind of worked in that space, you would be like, I don't even think I could do that. It's not even something that, like, if they can't give it to me, how could we ever work collaboratively? But it's possible.
All right.
I think this is, sorry, go ahead.
I was just gonna say, so get to the architecting, and what you told me after I had my shot at it, then I was like, how would you do it? And you gave me how you would architect it and what you would do with this PII.
Yeah. It's really interesting because unless you've worked in that space or worked with companies that have those kind of requirements, it's really just not something you would think of. It's just the concept of saying, okay, we're gonna make like a facility or a replica of the actual kind of workflow that you're running on a regular basis and showcase that. For most development, like for most developers, they're just the usual concept is, I want to make the actual thing. I don't want to make kind of a replica of the thing. But in this instance, in a lot of cases like this, it is actually a requirement. Like, there's just not really another way to do it. At least from my experience. But we have been very successful with it. We have a number of customers that have those requirements. We've walked through that entire process of building out those replicas, demoing those replicas, and actually helping to facilitate actually creating the real thing, the actual genuine article running in their environment. I think we've done it probably around 10 times or so up to this point, and it's been very, very successful. I don't think we've had a single instance where that the customer hasn't been able to do that.
You know, I love this because it's just a great example, another great example out of the many from the way that you think of how to solve a problem. So for example, if you have no notion or you can't do anything at the moment, what can you do? So, all right, it's an image classifier. Let's just say, for example, right? Well, I can make some dummy data and start there. And that's often a really good start for even like some of these tougher problems where you don't think about solving the whole problem, but let's start with like the simplest version of that model, right? The base case. What's this look like? Okay. And a replica in my mind is kind of like that. You're thinking, okay, well, I don't have the real data. I don't have the real, requirements, but I have the gist of what it needs to do. And it's a way to start moving forward versus just kind of, I don't know what to do. We need you to help us with this. And I also love that you mentioned how collaborative that process is. It must be a back and forth because especially when you're essentially onboarding them on how to productionize it, right? Using your services. That struck me as something that is pretty important. The fact that you need to collaborate a lot for that.
And you might not get it right the first time, and 9 times out of 10, you probably won't. I actually gave a demo yesterday. I actually gave a few demos, but I gave one demo yesterday where we were building out kind of a CI/CD pipeline, and we showcased it to a customer, and they're like, "Oh, this is really cool. but actually this is our specific like thing. Can we do that? And we're like, oh, that's actually why we gave this demo. We didn't actually give this for you to understand. We wanted to actually understand exactly what your workflow was. Because a lot of the times, if you just ask a customer like, hey, what is your actual workflow? It's hard to kind of frame that question because there's so many kind of unknowns in that space. Like they could be like, hey, we want this, but can we run this in this environment? Or we're actually using this other thing. Like it's very difficult to be able to extract all of that information because it's like it could just be like that one hidden thing that's like, oh, we're actually using this thing over there. We never would have thought of it. But giving a demo and building kind of a replica of like, hey, this is a way to do it. This is kind of if you want, you can actually just go and use this today if you want to. But just kind of like walking to the demo kind of sparks that kind of part of the brain in a lot of our customers to say, hey, you know what, actually, this is really, really close, but we're missing X, Y, and Z. And then we'll just be like, oh, cool. Okay, we'll just do X, Y, and Z. Here you go. Is there anything else that we need? And they're like, this piece too would be great. And then we can kind of have that continuing conversation to kind of really, really fine tune the demo into an actual eventual tool that the customers will be able to use to really, really take advantage of not only just their our product, but their overall machine learning kind of productionization workflow.
Awesome, man. So good. I want to thank you for coming. I think it's about time we wrap up. Before we do, I got to give a shout out to Algorithmia. They did not sponsor this episode, but they should have. we both got some cool swag from Algorithmia.
Right. Shout out to Diego. Shout out to Diego.
Yeah. And so, yeah, man, this has been so cool. Thank you so much for coming on here, sharing your wisdom. I knew it was going to be an incredible journey when you said yes to coming on here, and you did not disappoint. So awesome. I really appreciate it.
Well, I appreciate it too. Thanks, Demetrius, and thanks, Bam Bam.
Bam Bam, David. But it was such a pleasure, man.
Yeah. Adios, fellas. We will see you all later.
Sounds good.
Bye, guys.